readings. In this one, we'll be talking about an example of an induction proof. And the idea will be we'll have a sum of cubes from 1 to n. And it's supposed to be equal to the sum of the first degrees of naturals, again, natural numbers. From 1 until n, and all of that squared as a whole, which also means the parentheses itself is actually the sum of the first degrees, which can be written as this, and the whole thing squared. And we will also suppose we know this very popular formula. The sum of first degree natural numbers until n from 1 is exactly this. We don't have a proof for it now, but actually this is what we actually be using, because this itself not so imaginable to work with. This is a polynomial we'll be able to work with gradually as we explore what the induction proof entails. So for the induction proof, we see this formula tells us the follows, that the sum of cubes is going to be equal to the sum of the first degrees and all that thing squared, or we write it further using this formula that we're supposed to know. And this actually will be using, this is important, because this is a very popular formula. We're not proving it here, but we're just using it to rewrite this parentheses inside. Anyway, to do the induction, we first need a base case. N equals 1 we'll have here as follows. So n equals 1 basically means for n I plug in 1 and see if it works out on both sides for the same result. So k cubed, well, that is 1 cubed if I put it into the sum, and it should equal here again, I plug in 1, yes, that's right. So the case n equals 1 works out well, and then we want to do n plus 1 case. So the way induction therefore works is basically you prove for one case, but then you also prove that if I suppose n works, and I prove n plus 1 works, then for every following term it works. We proved 1. So therefore we will basically give a reasoning for why n plus 1 will work. But that will implicitly also give a reasoning for if n plus 1 works, n plus 2 works, and this is a chain effect. So that's the proof for all natural number inputs thereby. This is the idea. So to do it, we'll now consider the n plus 1 case. I just rewrite the base, not the base form is called the n equals 1, for example, but the initial formula that we're proving, so the formula itself, but instead of n, I'll be doing n plus 1. The k cube stays because that's not involving n directly there. So n plus 1 where there is n. And then I can rewrite these parentheses. I go until n, but I don't go just until n. I actually go until n plus 1. But this also I jump to our very further rewriting, which will actually mean this. This is what we'll actually be using for the proof. Now, why am I doing this further term or further case? It's because we went from 1 to n by default. Now we're going from 1 to n plus 1. We're proving n plus 1 case on both sides. We increase the n to n plus 1. Just replace every n by n plus 1. And now we will use the assumption that n was correct, that this thing was correct. And if using that we can get to this, basically the right hand side, using n plus 1, input it, plug in, then we've proved it. So let's see. This thing can be rewritten as 1 to n of k cubed, and the n plus 1 term is one more term, can be separated out by the property of sums to n plus 1 cubed on the outside. But we also have to refer back to that's allowed to suppose the case of n equals n was right, was working. We wrote it in a way that we actually got back again k 1 to n, which we know is this. So I write it there. Actually, yeah, this one, not this one here. That's where we want to get. And now, to finish up the proof, what we really, and again to reiterate the most important point, we're taking the k plus 1 case, rewriting in a way that we can find a bit of it that resembles the left side of the initial n case. Then we look, the initial n case, what it had on the right, replace that inside it. We see this side because this was this, we put there, and we see if this whole thing will actually equal to n plus 1 case on the right side, which is this thing. And this is a polynomial, if these two are equal, then it means we're fine and it's proven. So question mark if these two are equal, and there's a question if we're actually going to work this out or not. I can leave it up to you to check, but it's actually already checked. I checked it and it works out. These two polynomials turn out to be equal. Okay, these two turn out to be equal, and that means actually what you will get, the best way to look at it perhaps, or one of the simpler approaches here, is to multiply it all out into a polynomial. It would be a polynomial on the left side, polynomial on the right side, and it turns out all the terms are same. The polynomials on the left and the right side are the same. Therefore, it must be that this thing can be written into this thing, which is the n+1 case, written out using this realization on the right side. And because we got supposing that this n case is right, adding the n+1 addition necessity there, in total it gave us the n+1 case, equaling to it. That means that we supposed n is correct, and we showed n+1 works out through that. And we also showed that n equals 1 works. So by induction, we can have it seen as proven. n equals 1 works, and every next term will work as a chain effect.